YouTubers, how you doing? I know it's been a while since I've made a video, but I've been busy. So, without any further ado, it appears that I've discovered an interesting effect in space. Something I've never seen written about, I've never even heard about. But it follows principles of science that you all will come to, well, agree with, I'm sure, if you do a little bit of background and research into what I'm talking about. So, the question is, light speed travel, can it be attained? And of course the argument is Einstein's relativity, which, you know, nobody's even come close to really beating. So we're just going to go ahead and roll with Einstein, okay? I think it's a good idea. He was right. And unless we find a whole new set of constants that have nothing to do with, I don't know, reality here, then, well, and testable things. Anyway, so let's talk about light speed travel, or a light speed drive. And, you know, we think about faster than light drives, and it's like with Star Trek and the Millennium Falcon and all these other things, but we're human. If they're possible, I haven't seen any technology that really shows us that path that we can attain, at least in the next couple hundred years. However, there are some things we can do, and being able to travel to local star systems, I think, would be a good goal for us to make. So to do that, we have to think about, well, how fast can we get there? And if we had something that did take us close to light speed, well, how long would it take us to attain light speed? And what are some of the challenges that we're going to have to really look at when we do start to approach light speed? So let's start out with how we're going to do it. Okay, well, studying the properties of light, I found that we as a scientific race have found that light has some mass. And if you've been watching some of my energy videos, you'll notice that I have kind of defined light as a piece of an electron, and that electron, of course, having a monopolaric core surrounded by what appears to be dark iron that has made it through the shearing forces of a black hole due to magnetic flux line density. Magnetic flux line density. That's, you know, when it exceeds the shearing forces of a black hole. And they say it curves towards infinity, but I don't think it really, maybe in a mathematical sense, but as you know, mathematics are only proven as far as you can test them. So I think that there's going to be a threshold limit that you're going to exceed, which is the shearing forces. We'll just call it the shearing forces of a black hole. And I was thinking about, well, how do we get there? But let's think about light. We're going backwards, back to my electrosymmetry, where everything is essentially structured like an electron. You know, the universe as we know it looks like an electron, strangely enough. But let's not dwell on that, and let's just deal with the light. So the reaction that I found requires us to take an enormous amount of light and throw it out ahead of us. Now, not just as a shell, but as a beam. A continuous beam that goes off out into space in front of us. Few effects it's going to do, well, you know, you're like, oh, well the light's going to diverge, it's going to diffuse out, and it's going to be like worthless, okay, as a drive source. Well, kinda, but let's think about that. What if we took the index of refraction of hydrogen, which has a very specific index of refraction, and we tuned our laser that we're emitting ahead of us out in front of our spaceship, which is, you know, kind of cigar-shaped like this one, interestingly enough. That way we can emit our beam forward and backward, because we've got to be able to slow down once we get to the halfway point. And for this model, I've just kind of put the Alpha Centauri, you know, or just some random star, G-class star, that we're going to point the beam at. Now, there's some secondary effects that are that you can take into account. If we took a laser, say a 5 micron infrared laser, and we really carefully tune that to the index of refraction of hydrogen gas, we could tune that laser to use the interstellar hydrogen gas between us and another star as a lensing system, a collometer lensing system, to keep that beam together. Matter of fact, it could focus it down or really tight, which allows us to put an enormous amount of energy down a path that goes out ahead of us for literally light years. Now eventually, you know, if you did the math and you can figure out the exact point, but what you're going to do is you're going to have a system of mass that travels away from you at the speed of light, that is a beam of light. And you're thinking, well, light can't pull you. Well, if you have enough of it, it will. So I crunched some numbers here, and if, for example, you had a 10 octillion watt per second laser, that much photonic energy would exert a 1G force. Now 10 octillion, that's a ton, right? Yeah, that's watt, 10 octillion watts per second. So that much energy in free space is massive enough, it's equal to the mass of the Earth. And that's going to be enough to pull you through space. And it's going to be infrared. Now, like I said, if you used a beam system which had its beam diameter maintained by the index of refraction of hydrogen gas through interstellar space, it's going to take this beam of super concentrated energy, and you know, this is really hard to generate. But according to some of the more recent studies I've done, you could use a pod laser system. They used multiple large solid-state lasers that, incidentally enough, our most powerful lasers just happen to be in the long infrared range, which is what the 5 micron would be. It'd be very long infrared frequency. So since we can't produce 10 octillion watts per second, let's just think about something we can do, which is our fluoride laser system, just 50,000 watts. Okay? Now that's going to take a long time to generate any type of pinpoint 1G field. Oh yes, pinpoint 1G field. It turns out that the light, if stacked up long enough, exerts a force end to end. That rod of light becomes a 1G force pulling point. Admittedly, it's just a point, but it's a point of force across space-time. So you can hook onto that with your cigar-shaped craft. A couple other cool things it's going to do. It's going to clear the path of micrometeorites ahead of you. It's going to pull it down. It's that tiny, almost basically linear line through space is going to pull the micro dust down. It's going to create a dent in space-time, end to end, and also side to side. Now the side to side force is much less, but remember, it takes us a while to get there, and it's not going to be really fast. So let's go back to this 50,000 watt. If we used a 50,000 watt laser or a 300,000 watt laser, to get to 1 G force, it would take 1 quadrillion years. Whew. That's going to take a long time for our engine to warm up. And frankly, that might be too long for, well, the universe as we know it. So, might want to consider a little bit higher powers. You know, if we took, here's some other graphs right here. If we took the National Ignition Facility laser, we would need 25 million of them. Now, and that would take 5 years. Or is it 5 years? Oh, sorry, in 5 years, hold on. 500 trillion. Well, yeah, it would take 25 million National Ignition Facility lasers, which is our biggest laser that we have, and it looks like it's going to take, wow, it's going to take a while. It's still going to take a while. So, we're probably going to want to do a shaped pulse plate, or, like I said, this tube laser. Now, you want it to be a tube for a couple reasons. Like I said, the first reason is this beam that you're sending out using the principle, which of course I'm calling the Crespin Ratio, named it after my dad and his side of the family, because, you know, without him I wouldn't be here telling you all about this, and so congratulations. It's like trick or treat. You see the skeleton, it's all about the Halloween right now. So what I'm doing is, instead of tricking you, I'm giving you a treat. Now this treat might trick a lot of people because they're not really as deeply rooted in physics and science as I really spend a lot of time mentally. You know, I might, you know, forget to tie my shoe because I'm busy thinking about this stuff. So, So if we had a bunch of natural condition facility lasers, it would take a lot of them, but it still is possible. It would take 2 times 10 to the 30th 5 megawatt lasers to be able to produce the 1G pulse, or that would be in a pulse situation like this. This is a shape pulse, which is more like what NASA keeps talking about. They're like, oh, we're going to emit something ahead of us, and it's going to drag us along. Well, you're going to need a bunch of them. You're going to need, where is that? 2 times 10 to the 30th, 5 milliwatt lasers. So it is possible. 2 times 10 to the 30th, that's a big number. It might take a while to make those. So you might want to think about a big oscillated plasma cavity, or, you know, I was reading some stuff on some laser weaponry, directed energy weapon stuff. Very interesting plasma lasers, using electrons, just converting those electrons directly into laser output. With enough funding, you could make something like this. Of course, you'd end up with a, I don't think you'd want the multi-mode. I think you're going to want TM00. Although that might work too. So, emit the laser. Let's talk about some of the things that you're going to have to do or realize. There's a ton of stuff on here. So the Crespin ratio is the ratio of the angle of incidence that takes hydrogen gas and shows you what frequency laser you need to emit. That's the Crespin ratio that I'd like to name after my father, because he's just really cool, and he loves this science stuff too. So if you had a laser that was emitting around 5 micron, and then I think that's going to interact with the gas pretty well, you're going to end up with a very tight, narrow beam that is self-collimating down the length of the beam, all the way down to whatever you pointed at, a star or whatever. Now, if you, for example, were to emit a laser beam that had the capability of maintaining its integrity from, say, Earth to, I don't know, Alpha Centauri, would the gravity well, if pointed at another gravity well, if I have this stick gravity well, and I'm pointed across space-time, and I pointed at another gravity well, would they connect? Would the force of that sun backfeed down that strand, that string? And I'm thinking it would. So in about a year or a year and a half after you start emitting this beam, this powerful beam at Alpha Centauri, infrared, when it reached Alpha Centauri's gravity well, it should, based upon spatial compression and space-time denting and gravity and all that stuff, it should backfeed down that, all the way to your ship. All the way to your ship. Well, it would take another year. So it's going to take like 2 years, 2.5 years for the energy from that star to pull. But you got to think about it a different way. That pull, that energy star is emitting, or the energy from that star is emitting, the pull is constant. I mean, it already has shaped space. So as soon as your gravimetrically backfeeding line penetrates that space, its sphere of influence, as soon as it reaches it, which is still about 2 years, 2.5 years, it's going to backfeed down your beam. And it's going to pull or add additional pull down the beam. So you're going to end up basically using an infrared laser that's tuned to hydrogen gas, index of refraction, to create an ultra powerful. Now, you think about that again. Okay, so if I've got this super powerful laser that I'm shooting off here, and it's going all the way to Alpha Centauri, everything along that path is going to do what? It's going to melt. All the micrometeorites, and that's what's really nice, is it's a self-reciprocating system where the micrometeorites and everything else. Now, you think about that. Well, what good is that going to do? Well, now we have an endless source of what? Materials. We will have, and what is it? It's molten. So we have molten, or it's going to be hot. It's going to be hot, or at least melted together. We're basically going to have an endless source of iron that we can gather. We might even be able to use it as part of our propulsion here, but we should probably, maybe as we go along, we should make other ships and send those off other directions, or add to our ship, or add to its shield. Either way, you're going to have a stream of particles. Now, there's two things that happen, though. That's what I was looking at. There are some particles that are going to be pushed in, but if you look at the way the beam is working, you could use the beam, its diffusion, to clear the path ahead of you as well, a light year before you get there. You know, if you want all that stuff pushed out of the way, you could use the laser. But I think it'll also cause a collapse when you're using it in the proper way, which is to create a gravity well beam, a point axis beam of gravity between your ship and another source. So do you have to lock it onto another star? Yeah, probably. And you probably have to go all the way to the star if you really want to use it right. And of course, what's nice about a star is you get a really good hydrogen source there too, and other stuff. So see what else we got here. Not a lot. I mean, we got a lot of numbers and stuff where we crunch some stuff. We got some equations about infrared and time over distance divided by time 2. Or over time 2 by distance 2, S1 of C1, which is your ship of C1, and then the G of V, which is a gravimetric constant, velocity by velocity divided by velocity meters squared. If space over time, or space times time, and distance equals velocity times time plus half of. All right, so what we end up with is what's our good laser? Our good laser, according to this thing, would be 8.58 times 10 to the, well, that's, see, photons, 5 micron laser. Oh, 5 micron laser pulse. Now, see, that's the thing too. You don't need, because the beam. Okay, how long does it take to get to 1G? That was the other question too. And I think I answered it here. Essentially, it's a hydrogen gas fiber optic is what I'm calling it here. But it's interstellar. It uses the interstellar hydrogen gas ratio to create the beam. Now, admittedly, this could also be weaponized. If you had to shoot at other planets, I'm sure you could do that too. But you probably wouldn't do a lot to a planet with something like this because it's infrared anyways. All right, but what's nice about infrared is it penetrates the dust. It'll penetrate the dust. It'll go all the way over there. So this cigar-shaped craft, which we have are essentially our electron beam converter. It converts electron beam directly into, or an oscillation of plasma, into direct laser output, which is similar to the Apple system. If you've looked up any of the Department of Defense laser systems, that's the Apple system uses a direct conversion as well. If you look up solid-state lasers and you look up directed energy weapons, you look up the Apple system, you'll see that the Apple system is very similar to this. I drew this before I even read about the Apple system. I'm like, I wonder if they made that. Sure enough, they did. So there's an Apple laser module system that they're using. That's what they call it. It's an abbreviation for it. All right, so let's go over some of our watts. Okay, here we go. Here's my numbers. That's what I'm looking for. If 20,000 watt laser is used, then in 15 quadrillion years you'll reach 1G. If 1 year to 1G, you need 302 sextillion watts. If only 1 second, you need 9 octillion watts. And that's a lot. So basically, we're 9.5. So 10 octillion or 9.5 octillion watts per second equals 1G. That's, if you want a 1G field right in front of your ship, you're going to have to emit a pulse of light or half, or it's about half, 1/3 of that of electron-based energy, and you'd be able to drag yourself along with a radio frequency pulse as well. So this study of science is something that you can kind of like say, well, what if I have a really powerful radio emitter, you know, a cavity that spins it up and spits it out in a gigantic pulse? Well, aside from it killing everybody on your ship, or if any of that stuff got reflected at all off of meteorites and it came back at your ship, we would light you up like a damn spoon in a microwave. So you may not want to do it with RF or radio frequency. Light is kind of nice because it doesn't penetrate as easily, and it doesn't just turn you into a fireball. This right here, like I said, it's gonna be pretty cool when it comes to getting you from one place to another. There's some other equations on here, and if you look at all this stuff, you'll figure it out, I guess. The cool thing, I guess, though, is you get this this laser beam using the Crespin Ratio, which is the hydrogen to laser frequency, hydrogen index of refraction to laser frequency needed to maintain a beam diameter over light years. And of course, when you maintain that beam and you have all that energy stacked up and that really, really long point, now we could probably test a small version of that here, or maybe not, because we don't have enough distance here and there's too much interference here. If you're out in space, you can do different things. So, unfortunately, we're going to need a really, really powerful laser, a super powerful source of energy. Now, I did recently see a diamond power system, diamond graphite power system or something like that. That was really kind of cool. And that kind of follows with the systems I'm thinking of for, it's like a 5,000-year battery. Well, that's pretty cool. Or 5,000-year power source. That's pretty cool. I think we should probably look in that direction. Diamonds are definitely the future of optical computers, multi-layer optical computers. You think computers are fast now. Computers are not even fast yet. Wait until the future. In the future, there's crazy, we talk about index of refraction, crazy index of refraction based vacuum deposition laser layered cores. Man, those things are cool. Those are going to be really neat. You're really going to like those. But that's like way off in the future. So, for now, let's talk about using lasers to send a craft through space. Now, could you use it for, inner solar system travel? And the answer, of course, is yes. Definitely yes. I mean, they may say, well, you've got to have something to bounce it off of. I mean, I've seen some laser sail, cool ideas, stuff like that. But this goes beyond. This would get you to Alpha Centauri in 3 years? 3 to 5 years? 3 to 5 years to Alpha Centauri. That's fast. That's hauling ass. And that's part of the reason why we should look more deeply into this. So this is Lightspeed drive. I'll probably do another video on it. It'll be a different board, of course, so take it all in. This is the last time you will see it, because I have to do a bunch of videos on other stuff. But this is cool. Next I'm going to go into electron structure a little bit more deeply. Even though electrosymmetry kind of covered it, it's essentially a reboot of that video, so I can more deeply explain what electrons are, what photons are. I mean, electrons and photons, they're the same material, but we really got to talk about where they're getting their building materials, and that right there, that's for a future thing. So if we understand electrons better, if we understand photons better, and what they really comprise or consist of, I mean, we're going to make huge leaps as a species in science. Right now, we're dealing with it more as like cosmic fluff, and it's deeper than that if you look into photovoltaics. Einstein was there. Einstein was there. He knew it. He knew it. He saw it. He saw these reactions, and he saw this in photonics and photoelectric effect, and he's like, huh, that's really cool. And he wrote a bunch of stuff. It was a very interesting subject for photoelectric effect for him. He wrote a paper on it, or more than one paper. But I mean, the photoelectric effect, it kind of opens the door. It says, hey, photons strike this photoelectric material and it emits a photoelectron. That process right there, knowing why it does that. I've covered that in one of my other videos. However, that's super important. We should almost do like an entire video on electrons to photons, so we can better understand how to make one of these giant lasers, space drive lasers that can drag us through space. So let's say we got the Starship Enterprise and we have our nacelles, and we shoot those huge ass lasers out in front of us. Well, according to what I'm seeing here, that beam becomes a congruent gravimetric entity. It is a bonded by gravity thing in space, as long as it maintains a certain density. So we have to create an output that is high enough and pushes high enough down that cavity. Essentially, we're creating this continuous light arc cavity that pushes out into space ahead of us and is angled just so, and the frequency, when we say angled, it's the frequency. Adjustable infrared frequency versus the index of refraction of hydrogen. Those two things, and we got to make it adjustable, we got to make it tunable. We have a big tunable plasma cavity here, and we're going to take that and we're going to tune and emit that beam out ahead of us, and we're going to sit there and we're going to play with the tuning so that the point, this tunable plasma cavity, this gravimetric thing, we're basically going to be pulled along by gravity. You know, hopefully 1G, maybe faster. If we were to emit more power, now remember that this is the total cavity. This is per second. So you think, oh, 10 octillion watts per second. Yeah, that's per second if you wanted a 1G field from just light dragging you along. Okay, and that's if we go and we take the mass of a photoelectron, that's what I traced all that back to, and we figure out how many photons, or I should say I figured out how many photons it takes to make a photoelectron of an electron's mass size, and then these calculations came out of that. So they're correct or really close. I mean, I did some pretty big numbers. That's a big number. Look at that thing. All right, that's crazy. We did a bunch of big numbers in here. So if we were able to push more power down there, and remember, it's every second, and that cavity, that entity, that gravimetric entity that we're pushing out ahead of us, this light-based massive object, is going to drag our craft along. It's going to drag our craft along. And there's a couple cool things it's going to do. Now, we know that when an object travels really, really fast, its mass increases towards that of infinity. And we've tested that. We know it works. We have totally looked at that, and we know it works. So, why does it work? Well, remember what I talked about in my other videos was transverse binding energy through the universe. Transverse binding energy through the universe, when you go fast enough, you are exposed to enough of that passing through you. As the rate increases, it causes your nuclear structure to pull together. Causes space to compress. You and everything inside that, and anything that's traveling that fast compresses. As mass curves towards infinity. So, as this thing travels, it's going to become structurally hardened. The people, anything on this object that's influenced by that beam is going to be influenced to a point. As it travels down the beam, it's not just the Earth. It's not just the Earth. Now, admittedly, look at the Earth. The Earth travels through space, and that travel through space sets the binding constant for all chemical reactions and molecular, everything, nuclear, everything is set here by the travel of the solar system, the travel of Earth. I mean, everything is speed. Speed times speed times speed times the solar system speed times the galaxy speed. And the fact that we're anchored, right now, we are anchored in orbit of a black hole. That, just that is very interesting to me, because according to all of my research that I've seen about being in the direct influence of a black hole, being within its gravimetric shroud, according to the physics that I read, time's supposed to warp. It's supposed to go backwards. So are we actually going backwards right now? Even though we see the universe progressing forward? That might be a possibility. But let's just worry about travel right now. Time travel. Physical travel. Because when space compresses, you are what? When you compress and you travel towards the speed of light, you are removed from what time? So as this craft travels away from the Earth, this and everything on it pauses in time. The Earth, it stays where it is because its rate is equal to its velocity times its mass. And that, of course, is over time. And your ship that travels is going to have a different velocity and a different time and a different mass. Everything's going to be different. It's just going to be totally different as it travels out there, out across the cosmos. And that ship, we were looking at some time here on how long it would take to get to, we got some distance coverages here. We got a lot of different things here that I was discussing. But What's really neat is that we can tune that laser and we can emit that beam and we can create essentially a gravity drive from laser light. And that's, whoa, gravity drive from laser light, gravity drive from laser light, gravity drive from laser light, yeah. That's what we did. It's cool. All right, and once again, the more power you shove down that cavity, the more pull that cavity has on your ship. So you're going to go faster and faster and faster and faster and faster. And it might not take you 2.5 years, especially if that beam enters a region of space that comes in contact gravimetrically with an object that has already influenced that space. So let's say right about here, it influences that space. So right here, this is the point of gravimetric attraction to that star. So as my ship travels along, or say as my beam goes out here into space, whether it's a halfway point or whatever that star that's been emitting energy and curving space and time towards it, as soon as my beam encounters that, it's going to get a boost. And the larger the beam becomes, the more it's going to backfeed on my ship. That gravimetric entity known as, now you say, well, the light's really, really far apart. Yes, it is, but the light being coherent and of the same frequency, and the way I'm compressing it using hydrogen, we're basically making light soup. Really long. So it's like a noodle. It just goes out ahead of you. And that noodle has mass. Now, the mass isn't very much. However, the more we emit, there's another effect that occurs, which is something I wanted to save for the end of the video. The focal point out there in space, which is pushing against the hydrogen, you can make it reflect off of the tip and come back down. In other words, you're not even there. This is like way out ahead of you, and you're tuning your beam against the hydrogen gas, and you're tuning that frequency, and at a particular frequency, that hydrogen gas is going to be a mirror. Now your beam, is it doubled? Well, what if we emitted the beam through, let's say we emitted this beam through a dish, a concave dish with a hole in the middle. That means that any light that came back at it would be reflected back to it, and so on and so forth. So now we essentially have a giant lightsaber drive. Yeah, cool, huh? It's a little bit bigger. I mean, somebody asked me years ago, they're like, hey man, I need you to make me a lightsaber. I'm like, alright, well, let me see what I can do. And I got a few designs, but this is the first one that I've seen that uses the gas medium to reflect the beam back at the primary reflector, and then back and forth, back and forth, back and forth. So this 10 octillion watt per second beam doesn't have to be 10 octillion watts anymore. It can be much less than that. And this is the principle of the Crespin Ratio. So the Crespin Ratio brings us Lightsabre drive technology, which will eventually lead to drive technology here. So you can use it as a weapon, but you can use it as a drive as well. So there's all kinds of cool possibilities. So you start talking about, okay, can we do that with transparent air here on Earth? Should be able to. And it'll be all about frequency tuning. So the Crespin Ratio, which allows for this drive theory to be applicable, also allows for Lightsabre technology and structural hardening through spatial compression, which is pretty cool. We just need a reasonable power supply, which I believe they found with those diamond batteries. I was like, oh, those are cool. There's a lot of power there. Anyways, this is my video for today. Maybe we should talk about more about this Lightsabre drive. I guess that's what we'll call this video. Lightsabre drive. Lightsabre drive. Lightspeed lightsaber drive? I don't know. I mean, can you get to light speed with a drive like this? You can get really, really close. And I don't know about you, but I've always thought that, hey, if I have a gravity force that exceeds that of light's ability to escape, what do I have? A black hole? So essentially, if you make these things really, really, really good, you'll be able to take and basically project a conical black hole in front of you. And that's going to yank you along really, really fast. So, thanks for watching. And once again, comment below if you want to see more about this, or if you want to, move maybe into lightsaber technology, or move maybe into, I don't know, some more of this kind of stuff. Or, like I said, I still got to make videos about electron structure versus photon structure, and what are electrons, what are photons. But I know they have mass, and I know how much of their mass, of photon mass, it takes to generate an electron, which can be used for, well, electrical power. Like the light you see surrounding me right now. The light that allows this video to be seen. Those are all free space electrons that are being emitted and reflected off of me. And I don't emit light, but I sure can think about some pretty cool stuff. So, concave mirror, hole in the middle, shoot a big beam through it, and allow the beam to be reflected back and forth, back and forth. And maybe you start out small. You don't let it go very far out into space. But it does have to go pretty far, because you're going to need hydrogen gas. The more, I think the better, this will work better the higher the density of the gas. So this may have to be, I don't know, it may have to be a half light year long to be able to do interstellar travel. So this is essentially a light speed drive for interstellar travel. But if you scaled it down, it could also be a lightsaber. So lightsaber technology from the Crespin Ratio. Don't forget it, Crespin Ratio. That's my dad. He's really cool. He loves science, and this will probably make him happy too. Anyways, thanks for watching, and I'll see you again soon.